kind of a mathematical function that kind of gives you understanding of how important a certain feature is, for example. So that can be one weight. So there are different kinds of weights. So there is this ReLU weights. There is also activation functions which activate different nodes also based on the weights that are given. So if you have neural networks, because I was going to actually do a model for you, but I think we wouldn't have time. But uh, when you are modeling or programming, you will have certain functions that you need to write for the neural network, because a neural network just putting some layers is not going to work. So you have to learn a bit of what weights are and what activation functions are. But you also have functions that do error corrections. Uh, isn't symbolic AI just a structured set of rules? Not necessarily, because it can also be other things. Like I said, the semantic web, it is not a set of rules, it's a mapping of something, a mapping of your room, a mapping of whatever you want to be mapped. So it creates relationships, and because of that, it can do deductive reasoning. So, what I mean by this is, if you take normal programming, you have to explicitly program something to do something. Let's say you want to add uh, 5 plus 100 and something, and then you will explicitly write how it's going to be added. Or if you want to explicitly say this is a cat or this is a dog, you have to explicitly write whatever you are write, like whatever program. So it follows a certain logical process. But with symbolic AI, you do have rules, but you can do deductive reasoning, which means you can introduce something a little different and say, okay, now what? So this way it's able to use the rules and use the semantic web and kind of come up to a reasoning or a deduction, a probability basically. Please explain using a simple example if possible. Uh, what do you want me to explain, Pramo? Is it like, do you want me to explain symbolic AI or neurosymbolic AI? Symbolic AI system. Okay. Actually, I will be explaining it. You will see it right after this, because I'm going to dive into how neurosymbolic works. Okay. Yeah, I just wanted to show everyone as well now, like, research on neurosymbolic is really gaining importance, because we have large language models and we have lots of things happening with neural networks and deep learning, and we know we have a lot of issues or problems that come with it, and this is probably one of the ways to solve it. So it's gaining a lot of traction as well. Okay. So, yeah, examples of how neurosymbolic systems work, or how symbolic AI can be inserted to neural networks, actually, or how we are going to integrate these two together. So, one of these ways is you use symbolic inputs. So, knowledge representations such as knowledge graphs that have the same base of semantics and ontologies can be used as an input with symbolic rules to infer relationships. So, how knowledge graph works is very similar to how semantic web works. So, you have nodes that represent entities, objects, peoples, locations, and then you have edges of those nodes. And what you do is you build relationships between the edges of the nodes. So, once those are built, then you can insert it to neural networks that can kind of help encode these relationships and facilitate a certain generalization. So I think I have an example. Okay, so this is a symbolic mapping, by the way, and this is a knowledge graph. This is how symbolic AI is structured for Pramo if he wants to see it. This is an example. Okay, so let's look at like recommendation systems for movies. If you watch Netflix, you should know that they also kind of make some deduction, and you can see somewhere it says recommended, which means it's tracking what you have watched and it's kind of coming up with what you might watch. So, how we can make it a bit more stern, the neural network, or a bit more logical, in a way that it's not just deducing something just because of some random features and something that's going on in a neural network, but we are going to bring it some kind of sturdy factual information, so it's more into a logical process as opposed to what's happening inside the neural network, because we don't know. So we give it a certain set of rules or certain set of facts, and we drive it through a neural network, which will kind of help with the whole processing, and then you can come up with an outcome for, let's say, recommended movies. So for instance, let's say you have Tom Hanks, and we can say this is a node. Tom Hanks is a node, and from this edge, oops, sorry, from this edge to this edge, you have a relationship that says acted in Forrest Gump, and then Forrest Gump to drama. So these two are nodes, and that's a genre. So Tom Hanks acted in Forrest Gump, which is a drama, like the movie is in a drama movie. And you can also say Tom Hanks acted in Saving Private Ryan, which is a war movie. And this was directed by Steven Spielberg. So you can go on, like, you can create a really vast mapping, by the way, and the more the rules, actually the better, but this is a really simple one. And so how you would map this in, like in what do you call programming is, or how you would explicitly explain this rule, because now it's in a visual sense, is if an actor acted in a movie and the movie belongs to the genre, then the actor can be associated with that genre. So that is my rule that I'm giving to the neural network. So what I'm saying is, if this actor acted in this movie and it belongs to this genre, then this actor can be associated with that genre. So what it means is, it's going to make a deduction saying, if Tom Hanks acted in Forrest Gump, which is a drama movie, then maybe he also acted in other drama movies. So you might be able to find Tom Hanks in other drama movies. And since you watched a Tom Hanks movie, Netflix is going to give you other drama movies with Tom Hanks as well. So this is called deductive reasoning. And uh, why I said deductive reasoning, and why I think, like, why this is a neurosymbolic method, is because you can probably come to the same conclusion with a neural network, but you will never be able to explain how it came to that understanding. Because with this, with neurosymbolic, where you are explicitly explaining something, you can actually explain that, okay, the neural network came up with this outcome because of this reason. But if you are just writing a neural network and it's going to base information on something, we are not able to figure out what is happening inside a neural network. Okay, can't we say that mapping in symbolic AI as a learning process of that symbolic AI system, then it's essentially a learning based AI? Yes, it's true. So this, that is the second one, second part. So you can also put this as a knowledge base. That's what we call it, to your neural network as well. So this is one way. One way of making neurosymbolic is inserting symbolic inputs. Instead of it relying on all the data in the world, you're going to actually give it like a mapping of inputs, basically. And the second way is intelligent reasoning, which is actually where you will have this learning based AI, as you said. So you are going to, okay, let's see what we have here. Yes, symbolic based reasoner that can act as prior knowledge or rule based constraints to guide the learning within the neural network. So like you said, you can also use this as a knowledge base, or as prior knowledge, or as constraints to your system. And this will also help your neural network to a certain context. And one example is really first order logic. So first order logic is as simple as before as well, but with first order logic is that you are explicitly giving it some kind of facts, and that is going to be the prior knowledge, and it's going to be very simple facts. You are not going to overcomplicate it. For example, for all x, if x is a bird, then x can fly. So in first order logic, that's how you write it. uh, you don't have to complicate anything. So you are going to say, for example, for all x who are parrots, like let's say parrot is a bird, right? So parrots, if parrot is a bird, then parrot can fly. So it's very simple, and then you define what is x, and then you can also have more rules, like you can say if y is a human, then human can walk. So you have really simple rules that you can integrate as prior knowledge or as learning knowledge, or any kind of knowledge that you can put into the system, where it can actually do certain reasoning or have certain knowledge before going to a certain outcome. Okay, so yeah, you can also embed logical rules into neural networks. Neural networks can be trained to respect constraints defined by first order logic. So, if you can also use first order logic as constraints. So, you are saying a neural model that classifies images but respects logical rules. So, that means you're telling the neural network, okay, you can do the pre processing, you can use the data, you can come up with a certain outcome, but I'm going to give you a set of rigid rules and you have to follow them no matter whatever you're processing inside the neural network. So even if it comes with a certain outcome that is different from, let's say, what we have given as a rule, it still needs to follow that specific rule, because that's a factual rule that we have given to the neural network. For example, I have given, like, yeah, so cat is a mammal. So if you are asking is cat a mammal, and if the neural network is saying cat is not a mammal, but you have factually given that cat is a mammal, then it has to follow that rule. So this is also where the weights come into play, because the weight is like a threshold saying, you need to prioritize the rules as opposed to your answer, for instance. So this is also another way you can integrate symbolic AI with neural networks. Uh, yeah. So first order logic, which is really, really simple, you can see it now because in the past few years, there have been a lot of these models. So you have logic tensor networks that combine first order logic with neural networks to reason about data while learning continuous representations. Then you have neuro-symbolic reasoners, which are basically frameworks that use neural networks for perception and symbolic logic for reasoning. And then you have neural theorem provers, which is kind of a system that uses neural methods to guide the search for proofs in first order logic. If what I'm explaining is, if you want me to re explain it, also let me know, okay? Okay, so examples of neurosymbolic AI is like visual question answering, combining neural models to understand questions with symbolic graphs and factual reasoning. So visual question answering is basically you have some kind of image and you're asking a question about that image. Let's say you have an image of uh, a kitchen where you can see apples and oranges and knives and spoons. And then you're asking the question, what is edible in this image? And if you have explicitly mentioned that apples and oranges are something that's edible, then it will probably give you the answer. Actually, it will definitely give you the answer that apples and oranges are edible, as opposed to just neural networks. Because neural networks, what happens, it's a probability game. So whatever outcome that comes, you cannot 100% say that it's going to say it, because it's a probability, you don't know. Maybe 99% of the time it will say, maybe 95% of the time it will say yes. But with symbolic reasoning attached to the neural network, you can guarantee that it is going to say this because you have explicitly mentioned it. Then you have recommendation systems, neural embeddings for personalization, symbolic rules for logical constraints, and medical diagnosis, which is really important, I believe, because that's my research, because my research is in healthcare and robotics. Of course, in medical diagnosis, it's really important. I would assume that you would I hope that you don't 100% listen to GPT if it says, okay, if you ask it, I'm sick, I'm having fever, what should I take? And it's going to say, take Panadol or something. But if you ask a really complex question about medicines, and if you are somebody who has like allergies, or if you are pregnant, or if you have some kind of pre-existing condition and you're not supposed to take the medicine, GPT is not going to tell you that or ask you that. But you can build this kind of interactive communication systems where when you're asking about medicines, for instance, it's going to ask you more questions before giving you an answer. So these kind of systems are based on neurosymbolic AI. And then, of course, fraud detection, identifying patterns through neural learning while enforcing fraud rules. So if you have, let's say, in a company, you have documentation of rules and regulations that need to happen, let's say, in a industrial complex. Neurosymbolic is a really great idea because with symbolic AI, you can essentially build all these rules and put it into a neural network. So, fraud detection is quite similar because you have explicitly mentioned regulations. So, you can really map them out in the way you want, create the rules that you want, put it in the neural network, and it would be much more accurate, much more explainable, much more understanding. So, this is a really good place to use neurosymbolic as well. Uh, yeah, so symbolic integration to neural networks can depend on the problem that you're trying to solve and what outcome or advantage you are looking for compared to state of art methods. So, what I mean by this is that I'm not necessarily saying that neural networks don't work. I'm saying that symbolic AI with neural networks are much more interpretable, much more explainable. And if you want to understand how it came to a certain outcome, this can really help. And it's going to be more accurate contextually because you are giving it certain regulations or rules or representations. So you're explicitly saying something to the neural network. So if you want just a model that has really high accuracy and nothing else, then you don't necessarily need neurosymbolic. But for instance, if you want medical diagnosis, then you would probably opt to using neurosymbolic systems because it's much more explainable and you are explicitly giving it some regulations as well. Uh, yeah. So, as I said, the current challenges with neural networks, there are two big challenges. One is reliance on data and one is interpretability. So, reliance on data, what I mean is that even large language models, I think recently, even in WhatsApp, was it Sam Altman who said they're going to use data from WhatsApp groups, I guess. But the data that is used, it's really highly reliant on data because large language models are majorly natural language processing problems. So that relies so much on data. And the reality is, data is not 100% certain thing. It is very biased because you cannot have 100% unbiased data ever. It can be incorrect because whatever you type or whatever data that is given, you won't check one by one either. You have data scarcity, which means if you want, let's say, uh, all the cats who look like how they look in Sri Lanka will probably not be the way how they look in Finland, or similar for the trees. If you are only having data of all the trees in Sri Lanka, then you will miss out all the other trees that are there in the rest of the world, for example. So that is data scarcity. And hallucinations means inaccurate information because it has so much information, it's just going to give you some random thing because it doesn't know, it cannot reason, it doesn't have this reasoning capability. So reliance on data is one major problem, and the second is interpretability, because it's a black box, you don't necessarily know what's happening inside neural networks. So trust on a system is mandatory, but you cannot really trust neural networks. And then you have regulatory compliance, which is like regulations that maybe if you're a security company, like, privacy of data, for instance. You don't really know if it's, happening, like privacy is happening inside a neural network, for instance. You can do privacy, of course, like regulations and transparency. So these two are kind of these big problems. And with neurosymbolic, it can be one solution because it is explainable and it is giving more structure, more regulations to neural networks. Yeah, so this is kind of my presentation. Let me see, do we have time? Was it Tarushi? Do we have time for like a do we have 5 more minutes that I can quickly go through this Jupyter notebook? Who can I? Yeah, I can go through this really fast, I think.
Yes, Dr. Please do.
Yeah. Okay. So was it this? Actually, no, it's this one. Yeah. So what I simply want to show you here, this is a notebook that kind of shows you an advantage of having these symbolic rules. So this is for a loan approval process in a bank, let's say. And when it comes to these loan approvals, basically, if you are just creating a neural network, you're just going to give it information like you're going to give it approved information and rejected information. That means you're going to give some data of people who has approved these based on these factors or these features, and then rejected based on these factors and uh, features. And that can be so vast because if you are giving 100 features or 50 features, it can mean very different things, and you necessarily don't know what's happening inside a neural network. But if you explicitly say, let's say, you want to approve a loan if the income is more than 50K and the credit score is less than this and the debt is like this. So this is a necessary rule in any bank, for instance. It's an example. So in a bank, that's what they would probably check. So yeah, basically I created some data, created the data frame, and here I'm just showing the approvals based on three of the features, which is the income, the credit score, and the debt. So all these zeros means that it was rejected, and these ones are in the orange is like accepted. And you can see like based on the what do you call the feature, it differs really. And what I do is, if you have already know neural networks, it's quite simple. You just break the data into test and train, and then yeah, you split the data into testing and training, and then you do a prediction. And as you can see, the prediction with neural only is like 90%, which means 90% of the time it's accurate, and the other 10% it's not. And you can see it here in the accuracy. So what I want you guys to look clearly is that um, the out of the 186 rejections, 180 was correctly seen by the neural networks, but the six were falsely seen, because that's why it says the true label. So the rejected ones, which were really rejected, is like 180, but the rejected ones which were approved is six, which means there were six cases that were not correct. But if I add this rule saying symbolic correction, so I'm going to add this rule saying if this person has this kind of income, this kind of credit, and this kind of debt, then you have to follow this rule explicitly. So it says that I'm going to override this false positive. So if you run this neurosymbolic test again with this prediction, with this symbolic rule, then it becomes more accurate. So it becomes 0.935. And you can see here then all the applications that are supposed to be rejected is actually going to be rejected. So there isn't any rejection applications that were approved. So this is a very, very, really simple, really simple notebook I quickly made just to show you that
We
uh,
cannot
giving it. giving it some kind of structure really helps. But yes, somebody had a question? No? No? Okay. Uh, but yeah, that is it from me. Um, if you have any questions, feel free to ask me. Uh, yes, I can give you the presentation slides and the Jupyter Notebook link. Not a problem at all. I also have a notebook for semantic webs, but it didn't come out properly because I was in a rush. But I can even send that to you as well. So you guys can have a look. It's, it's doable. Yeah, feel I think you had a Slido, I guess, also. So you can ask me questions. And yeah, that's it from me. I can, did I? Yeah, I also made a slide about myself, I guess, because I think Tharushi mentioned that I should say a bit about me because I didn't. I just dove into um, the presentation. But yeah, I am, as you explained, I have two masters. So I graduated from Lyceum International School in 2016, and I immediately joined SGLA Graduate School of Engineering in France. And I did my engineering degree basically, and I got selected to this double degree program where you can go to another European country or European university, but that's also like based on how your scores are, what you have done, and basically your credits and everything. So I got selected to Obo Academy University in Turku, and I completed my second master here. And then through my master thesis project, I got selected to become a doctoral researcher. And yeah, that's where I am. And of course, I do some voluntary projects, which is like ESN Finland, which is Erasmus Student Network. That's basically funded by the European Union for the exchange students of all of Europe. And I am a member in ESN Finland team, and I have, of course, collaborated with all the 45 countries regarding this matter. And for ESN Obo Academy, which is a local section, I was the president in my mandate of 23. I was ambassador for Els Budge, which is kind of a community that promotes STEM fields to young female students all over France and also Europe. And then, of course, I was partnership manager and in the aeronautics club back in the day when I was in France, and of course, the basketball coach as well. But feel free to ask me any question you like. I think I gave my email before as well, so you can just email me if you want to learn something. And yeah, that's it from me. Thank you, Pramo.
Thank you so much, Miss Prashani, for sharing your insightful knowledge and experiences with us. Your work is truly inspiring, and the clarity with which you explain such a complex topic has made this session immensely valuable to all of us. So now it's time to hear from the audience. We are opening the floor for your questions and comments. Please post them through Slido, and we'll be bringing them to our speaker shortly.
Can I already start answering questions?
Yes, sure, madam.
Okay, so do you have any advice on where you start learning AI? Yes, I do, but I do. Do you have Coursera? Do you know Coursera? So Coursera has this introduction to artificial intelligence, and I can actually send you the person who does it. It's a professor by Stanford University. Actually, the way he explains it, it's so amazing. He explains everything regarding like how weights work and the mathematical process of it in a very kind of clear way. So if you really want to understand artificial intelligence, I would really recommend this course to you. Let me check which course this is. And if not, of course, you have YouTube, you have basically everything. If you just write introduction to AI, there will be so much of information. But I would recommend this Coursera course to you because the he is a really amazing professor who has done a lot of investigations and innovations. So the way he explains is it's really really clear. So let me check. Yes, exactly. He's Andrew NG. Yeah, so you already know it. Okay, so it's known as supervised machine learning regression and classification in Coursera. Uh, Actually, if you want to learn about artificial intelligence, I would suggest that you start with machine learning because that kind of is like learning C before starting Python. So you kind of understand exactly how neural networks are kind of coming into being, for instance. So I wrote it in the chat, machine learning. Because it has different learning methods like supervised learning and unsupervised learning, and then in supervised learning you have like classification, regression, and so on. So this is where you should really start if you want to start learning about AI, and then you can move on to neural networks because neural networks it's a little different, but this machine learning part is important if you want to understand like how AI systems are built. Mm, you can. I see the second question. Yeah. Thank you so much for the session. Na, na, na. Okay. Generative models with 3D related. You have you learned about this voxel based models? I think it's like GAN. So it's like 3D GAN. I wrote that as well. Uh, you need to if you want to learn about like 3D related, which is quite much about like visuals, you should learn about computer vision. So computer vision is somewhere you can start with, and then you can dive into like 3D modeling.
Yeah, thank you for the questions. And okay, so as a token of our heartfelt gratitude for dedicating your time and expertise today, so we would like to present a token of appreciation to Miss Prashani Jayasinghe. Your contribution has made a significant impact on everyone here, and we are incredibly grateful. Thanks again, madam.
Thank you so much for having me. I hope everyone learned something. I assume that you will not know. I mean, I'm pretty sure you know about AI, but I just gave you a speech from like the introduction, so that if you need some contextual understanding on artificial intelligence, I hope you got that. And I hope you also understood neurosymbolic AI to a certain extent. And I wish you guys all the best with your studies, because I don't know which years you are in, but like, yeah, yeah. Thank you,
Yeah,
everyone.
thank you, madam. So before we conclude, let's capture this moment together. So we kindly request everyone to turn on their cameras. The virtual background is already shared in the chat. All right, everyone, get ready. Let's count down. Three, two, one. Okay, so thank you all for being a part of this memory. So to formally conclude the session, I now invite Ms. Agalini Pushparasha, co-chairperson of Ingenuity 2.0, to deliver the vote of thanks on behalf of the IEEE WIE Affinity Group of the University of Muratua.
Good evening, everyone. As we come to the end of this wonderful session, it is my privilege to express heartfelt gratitude on behalf of Ingenuity 2.0. First of all, I would like to extend my sincere thanks to our esteemed speaker, Miss Prashani Jayasinghe, for sharing the invaluable knowledge and insights. Your expertise has truly enriched our understanding and sparked new ideas. A big thank you to all the participants for your enthusiastic presence and the active engagement. Your thoughtful questions and contributions helped make this session interactive and meaningful. I would also like to acknowledge the efforts of the organizing team behind the scenes. Your dedication and coordination ensured the smooth flow of the session from start to finish. Let's carry forward the learning and inspiration from today as we continue to grow and collaborate. Thank you once again and have a great day ahead.
Thank you, Ms. Agalini. Thank you to all the participants for your engagement and enthusiasm. We hope today's session has sparked new thoughts, inspired fresh ideas, and opened your minds to the wonders of AI. Signing off, I'm Janati Kodikara. Until we meet again in our next Ingenuity 2.0 session, stay curious, stay inspired, and good night.